honey.
Hasta la vista, baby.
And what's that again? Anyways, I will Google it later. Bye.
So being a T2 fan, I cannot help but translate. But I have to make sure that the translation is correct and within a short span. And more importantly, before my wife finds a bug in it. Hello everybody. So the motivation of our current work is somewhat similar. It is to ensure that the validation done by the binary lifters are correct, and to achieve this validation using a computationally cheap method. The traditional ways of doing this validation either instruments the lifter itself or they use heavyweight symbolic execution. Now, in this work we devise a novel method which mitigates all these problems, and more importantly, we find new bugs in a widely used lifter. I am super excited to talk more about this when we all assemble together virtually on 19th of June. So, see you then.
An invariant at a program location is an assertion that holds in every execution of the program when it reaches that location. Invariant generation is one of the most classical undecidable problems in program analysis and is a prerequisite for many other problems, such as verification of safety and termination. Because the problem is undecidable, we have to look into invariants of a specific form, for example, polynomial invariants. Previous works on polynomial invariant generation can be divided in two groups. They are either too costly and inapplicable to even toy programs, or are fast but do not provide any completeness guarantee at all. In this work, we bridge this gap and present an algorithm that provides both completeness guarantees and applicability.
In this talk, I'll be describing an approach for generating numerical invariants for recursive procedures. The approach combines ideas from two areas of the literature. First, template-based invariant generation, and second, recurrence-based invariant generation. Template-based techniques first specify the form of the invariant using a template that contains numerical unknowns. Then they find and solve constraints on the unknowns to obtain the invariant. The approach that I'll describe in this talk uses templates in which the unknowns are functions rather than numbers, and the constraints on those unknowns are recurrence relations. The approach finds invariants that include polynomials, exponentials, and logarithms, and it can be used to analyze procedures that contain multiple recursive calls, such as tree traversals and divide and conquer algorithms. The approach can be used to prove assertions and to find complexity bounds, such as an n log n bound for merge sort and a bound of n to the log base 2 of 7 for Strasson's algorithm. To find out more, please come to our talk.
A first-order quantified separator for a set of structures labeled positively and negatively is a formula which is true for the positive structures and false for the negative ones. We allow general quantification, including both universal and existential quantifiers, which is the key to the expressiveness of our technique. If we allow any quantified formula, however, then a separator exists whenever the set of positive and negative structures is disjoint. So we use the class of k-prenex formula, which are formula expressible k quantifiers in prenex normal form. We show both that the complexity of k-prenex separation is NP-complete and give a practical algorithm for its implementation. We further show the utility of separation by adapting IC3 PDR to infer invariants. We show that this implementation can infer the invariants for non-trivial distributed protocols. Take a look at our paper or come to our PLDI 20 talk for all the details.